Nik Bear Brown. Build it with a CLI, then take it apart. The model was 94% accurate in Python. After the toolchain got done with it, it was 91%. And nobody could say where the 3% went. Quantization is the obvious suspect, but toolchain-induced accuracy loss is a separate failure. An unsupported op fusion, a range mismatch, a CMSES-NN fallback that silently changes the output. The only defense is a diff at every hop. Bisect which layer introduced the divergence before you blame the wrong thing. Ask for the experiment. In the terminal, Claude, write deploy runner.py, convert a Keras model to TFLite in T8, run the TFLite interpreter on a validation set, compare it to the float model, and bisect which layer or op introduced the largest output divergence. Read it before trusting it. The bisection walks the network layer by layer and compares the float model's intermediate output against the TFLite interpreter's output at the same point. Divergence is mean-squared error between the two. A small divergence is normal quantization noise. A spike is a toolchain failure, an unsupported fusion or a kernel that rounds differently than the float version. Run it. 10 layers plotted left to right, divergence on the vertical axis. Layers 0 through 6, small bars, normal quantization noise. Layer 7, a crimson spike. MSE jumps by 2 orders of magnitude. The bisection localizes the leak. This is the layer the toolchain broke, not quantization in general. Layer 7 is the spike. Now find out why. Iterate. Claude. Add a per-op supported and unsupported check for CMSIS-NN and flag any fallbacks. Rerun with op support check. Above each layer bar, a chip appears. OK for layers with CMSIS-NN kernel support. At layer 7, fallback. The op at that layer, a fused activation that CMSIS-NN doesn't support, falls back to a reference kernel that rounds differently than the float model. That is where the 3% went. The 6-step deploy pipeline breaks silently between steps. Quantization error is one thing, toolchain error is another. The bisection separates them by walking the network and measuring the divergence at each hop. The CMSIS-NN op check explains the mechanism. Fix the op, rebuild, and the 3% comes back. Your move. Bring a trained keyword spotter model in Keras or TFLite format and a validation set. Claude can't train these, but given them it does the conversion, bisection, and op check in pure Python. No hardware required. The output beats in this video use illustrative divergence values. Run deploy runner.py on your real model to get the honest layer-by-layer diff. Nik Bear Brown. Build it with a CLI, then take it apart. At Nik Bear Brown, nikbearbrown.com.